So the new section is activities. New section for exam 3. And the idea here, the thinking is that these ions in solution, that they interact with each other. And when we're talking about concentrations, concentration is like moles over liters, right? We're assuming that everything in the solution is nice and homogeneous, right? Perfectly spread throughout the solution. That's the identity, that's the definition of a solution, in fact, right? It's perfectly homogeneous everywhere. Well, that's not the case if you have ions, because they start sticking together, right? And you get solvation effects, and the more ions you have present, and if you use concentrations, you get even a larger error. Error. Concentration is everywhere, right? We haven't used Henderson-Hasselbalch equation, but Beer's law, the equilibrium constant expression, solubility, Ka, Kb, Ksp, Kf, they all have concentrations. All wrong results if you have ions. Now, when do you have ions? When do you have ions? What type of compound? Ionic compounds. Cations, anions, sulfate, phosphate, sodium ions, potassium ions, right? All that kind of stuff. Sugar? No, molecular. So we don't care. Concentration works. That's kind of where this is heading, right? Because concentration, sugars, it's not going to interact with anything. It doesn't have a charge. Okay. So there's this term that we need to talk about. I kind of think of it as the chemical environment, but we call it ionic strength is the technical word for it. And here's our solubility rules, or one set of solubility rules. What would be an example of some insoluble salts in water? Looking at those solubilities rules, Marlena, what would be an example of a insoluble salt? Something that forms a precipitate. All right. She says, what was that? Ca, what something? Carbonates? Okay. They'll form insoluble. So she wants to work with the carbonates. Great. We just need a cation to go along with it. What could it be? Somebody help her out? Okay. Ashley? Ashley? I hear sodium's a cation. You like that cation? Well, don't work with that one. What's the cations that you put with anything? They're always soluble and always aqueous. They always dissolve. Sodium's one of them. Sodium, don't use those. Sodium, lithium, potassium. Pick anything other than sodium, lithium, potassium. Magnesium. Okay. And then there's usually some tricks. So you check to make sure magnesium isn't one of the tricks. It's not. Ammonium and alkali metals are. So magnesium. All right? So you remember doing this? The charges go down there. But it's an ionic compound, so what happens to the 2's? They go away. They cancel out because it's an ionic compound. It's a crystal. You want the simplest ratio of those ions. Okay? Let's make sure you're reading this table right. Sochi, give me another example of an insoluble salt. Another example of an insoluble salt. The phosphates? Okay, the phosphates. And what cation could you use with it? I couldn't hear. What'd she say? MG. MG again? Oh, come on. Copper. I don't care. Everything up here is a metal. Zinc, aluminum, pretty much everything up there is a metal. You just have to know its charge, right? Otherwise, I'm supposed to write it up here. Otherwise, you can't write the formula right. Right, a 2 and a 3. Okay. Good question. How, like when I said copper, I technically should have said copper 2, because you're right. Those transition metals, they can, for all intents and purposes, they can really take on any charge. Now, that's not totally true, but there's a range of charges. So that's why you got to say copper 2, copper 3, iron 2, iron 3. But we never did that for groups 1 and 2. Why? It's always group 1. Sorry, group 1 is always plus 1. Group 2 is always plus 2. So we never said calcium 2. It was always just calcium ion. Okay? But pretty much everything else up here, chromium 3, vanadium 5, you have to give the charge.
We can just pick out whatever charge you need in that situation.
Well, like copper, there's reasons why only copper 2, copper 3, and I think copper 1 exist.
So you couldn't make it like copper 3 and then only add it 1 to 1?
If copper 3 did exist.
Oh, it does exist.
But yeah, it does exist. But if it was a copper 3 ion, it has to be a copper 3 ion.
Okay.
I could grab a bottle of, I don't know, copper 3, get it to be soluble. It'd have to be like a chloride or something. I could grab a bottle of this stuff, and I wouldn't have any copper 2 or copper 1 in solution. I'd only have copper 3. So the charge is really kind of fixed. And that charge has to go down, whoop, it's a 3, so that would have to be a 3. Simplest ratio. So you guys remember doing this stuff? Okay, a little rough. But we're not going to use the solubility rule so much anyway, but it's good that you kind of remember it. So these guys are supposed to be solids that we named. Copper 3 phosphate, magnesium carbonate, they're solids. They're supposed to be insoluble. But we worked with some KSP problems, and we found out that, oh, they actually dissolve a little bit, and the solubility is Xn ice of the KSP reaction. Great. And we do that. But you can get the wrong answers. How can the solubility of an insoluble salt, any of these, be increased without changing its KSP? Increasing the ionic strength. What are you doing to increase the ionic strength? Now there's a hint. Like, yes, we're manipulating the solvent. Like dissolves like. These guys are ions, right? And you know, we're always talking about water, okay? How can you change the environment of water? Manipulating the solvent. What can you do? Changing the ionic strength. That's right. That's a technical jargon. But what would you actually do? You could, well, pH. You could adjust pH. That might help. But add some ions, right? Now, you can't add, if you're talking about increasing the solubility of copper 3 phosphate, you can't add copper 3 or phosphate. We're not talking about a common ion problem. We're talking about, hey, let's just add some potassium chloride. Right? Add a lot of it. Because does this stuff stay as a solid? No. It's going to completely dissolve. Is there a common ion? No, because we're talking about copper 3 phosphate here. There's no common ion, but yet more of this copper 3 phosphate dissolves now. Because we have a lot of these potassium ions and chloride anions floating around in solution. There's a lot of it. We just changed the chemical environment. It's more of a charged environment. Right? Does that make sense? And like dissolves like. So if you make the solvent, manipulate the environment of the solvent by just increasing the ionic atmosphere, making that environment more charged. You bet. Like dissolves like. So more copper 3 ions, more phosphate ions, it'll dissolve more. Solubility is going to go up. And the more KCl you add, dang, yeah, it'll go up even higher. That makes sense?
So it's like there's more ions like floating around, so there's more like interactions, and so it breaks up more soluble.
Yeah, it's to me I like the rule of that like dissolves like.
So what do you?
So in other words, what is this copper 3 phosphate? What is it like? It's very what? Polar or non-polar?
Polar.
It's extreme polar because it's not even polar. It's charged, right? It's way on the end. So if you can make whatever solvent you can do, if you can manipulate it and make it more like polar, man, it's going to dissolve even better. And that's all we're doing by adding potassium chloride. The technical jargon is we're increasing the ionic strength. That's the technical jargon. Make sense? So if you calculate X in ice with potassium chloride solid there, you had better get a bigger answer. Now this, put it into effect of something that's life or death. You have a salt that's a solid that you have to consume. right? And it's a salt that controls someone's heart rate with their right? Right? You want their heart to be beating at a constant rate. They take this solid. Man, I would not use concentrations in that calculation to see what their dosage is or to see how it's metabolized. You got to take into account ionic strength, because you don't look at the stuff in your blood. It's not pure water, anything but. So you need something to take this into account. This idea that if you change the ionic atmosphere, that has direct consequences on ions in solution and how much is there. Okay, so that's the whole game plan for today. How do we handle that? But we're not quite there yet. We want to, I think, first here, calculate ionic strength. Okay. So what does ionic strength refer to? What is this little symbol? Mu. How do you spell mu? Mu? M-U? I don't know. But mu, right? Okay. So here's one way to calculate it. Probably the only way that we're going to see. 1/2. The big sigma symbol means do what? Summation of. Add it all up. Okay. CI/ZI squared. Okay. So you have all these ions in solution. Remember, if you don't have any ions, forget it. There isn't any ionic strength in the first place. So we have to be talking about ions. So you could have, let's see, identify them all. You had calcium, you had chloride, and I don't know, maybe you had some sodium, and some phosphate. I'm just picking some ions there. Okay. If you have this solution, how would you calculate the ionic strength of it? 1/2 the summation of CI times ZI squared. Well, what's the CI and the ZI? Good. CI is the concentration. And what's the ZI? Mu is the ionic strength. What's Z? They're going to be constant. They're going to be consistent with this. Z is always going to be charge. Kind of nice. And you're squaring it, so do they care whether it's a -3 or a +3? No, they're squaring it. And that's all for the ith compound. So in this case, if we have 4 different ions, we're going to have 4 terms in the summation, right? 1/2 times the concentration of phosphate times its charge squared. 1/2 times the concentration of chloride times its charge squared, plus 1/2 the concentration of sodium, right, times its charge squared, and 1/2 the concentration of calcium times its charge squared. Make sense? You just add them all up. So let's try it. For this one, we have 0.001 molar sodium chloride. So identify all the ions. All right? We're going to have to figure out what sodium is, what chloride is, plug them into the equation. I have 0.001 molar sodium chloride, Jessica. What would be the concentration of the sodium? First, is this stuff even soluble in the first place, or is this an ice problem? It's 100%, right? Where's just it? Who am I picking on? Well, just the concentration of sodium. What would be its concentration? .001. Does everybody see why? This stuff is completely soluble. It breaks up completely into sodium ions and chloride anions. So it has, yeah, the concentration of sodium has to be 0.001. Everybody, would be the concentration of chloride. Same thing. Okay. So mu, 1/2, right? Concentration, 0.001 times, I don't know, the charge squared. And chloride, 0.001, -1 squared. Negatives really don't matter, right, because you're squaring it. But so that 0.001 plus 0.001 divided by 2, you get 0.001. Make sense? Can you... Well, I think before we make a generalization, let's do this one. Go ahead and do this next one. 0.1 molar sodium sulfate. Identify the ions, identify their concentrations, calculate the ionic strength. And then we'll step back and take a look at, see if we can make a generalization here. Yeah, because it's a sodium. Yeah, because it's sodium compounds. This is going to completely dissociate.
So the charge is the same. I mean, the concentration is the same. Multiply the 2 times the initial concentration.
Yeah, that's what we're after. Just make sure we can see this. What's the charge on my sulfate? -2. Let's say you forgot. Oh, I remember it's sulfate. It doesn't really matter if you remember the name or not. But what's the clue to say what the charge is on the sulfate? Yeah, good. You're remembering this. Good. So that's why the 2 is there. What did you write down for the concentration of sodium? 0.001?
Times 2, or do you raise the 2?
No, we're not raising it to any powers. We just want to figure out what its concentration. Because raising things to powers, that's all with equilibrium constant expressions. We just want to figure out what its concentration is. Maybe break it up. If you have 1 unit of this, how many units of sodium do you get?
I divide 2.
You get 2, right? If you have 1 unit of sodium sulfate, how many sulfates do you get? 1, right? And if you're not sure, I mean, we never write 1s. But yeah, there's just a little 1 down there. So we get 1 sulfate. Okay. So if you have 0.001 molar sodium sulfate, you said you get 2 units of sodium out of it, 1 unit of sulfate. What must the concentration of sodium be? 2 times that. Because you get 2 sodiums for every 1 of the sodium sulfates. So if you get 2 sodiums, this has to be twice the concentration of sodium sulfate. It all breaks up completely. 100% soluble. So this has to be 0.002. Okay. The concentration of sulfate must be 0.001. You only get 1 of them. It's 1 to 1, right? 1 sulfate for every 1 sodium sulfate. It's 1 to 1. You know, if you weren't sure, you could actually do it this way. 0.001 moles of sodium sulfate, and then in 1 mole of sodium sulfate, how many moles of sodium? 2. So that works that way too. Okay, it's the same idea. And I'm just going by the chemical formula. Okay, so now we got to plug it into our ionic strength equation. 1/2 times the sum of the charge of each ionic species times its concentration. Charge squared times concentration. See what you get. Jose, did you get an answer? No? You got 0.003? 0.0045? 0.003? Yeah, 2.00. Okay, a lot of folks are getting 0.003. Hopefully that's it then. Anybody else get that? Okay. So why did I put units of molarity on here? It's just following from the equation, right? Concentration. Yeah. Well, it's just following from the equation. So the units you end up with is molarity, because that's what you had your concentration units in. Now, before we move on, I want you to notice something. is sodium chloride, can I call it a 1-to-1 salt? Can I call it a 1-to-1 salt? Yeah, because there's 1 sodium for every 1 chloride. Can I call sodium sulfate a 1-to-1 salt? No, 2-to-1. It's not 1-to-1. We could do part A. Just imagine if I change NaCl to HCl, strong acid. Change it to KBr. Change it to any salt or anything that's going to break up 100%, 1-to-1. Would that change my final answer? Right? Look at it. Everything's 1-to-1. Everything's 1-to-1. So even if the charges were +2 and -2, right? We're still dividing by 2. Let me think this out. I know the +1 and -1 work. What I'm trying to do is make a generalization of going from here. You see the concentration of the stuff and jumping right to this. I'm pretty sure it only works for +1 and -1, 1-to-1 salts. So you really don't need to go through all this if it's a +1, -1, 1-to-1 salt. You know its concentration. It's completely soluble. Boom. You know its ionic strength. It's the same thing.
The 1-to-1 is only about the charge, not about like the number of...
I think it has to be +1 and -1.
Yeah.
Otherwise, I don't think it's because you're squaring those 2's, and then you're going to be dividing it by 2. You end up multiplying it by 2, so you're not going to get the same answer. What's that? Yeah. So you have to have 1s for subscripts. Have to have 1s for subscripts. But it also can't be. Notice 1s for subscripts is this. But that isn't going to work. That's not going to work. Right? That's a 1-to-1 salt, but that isn't going to work. So it's, I don't know, it might be confusing things by trying to save you time, right? Just calculate ionic strength all the time. You won't worry about it.
With the molarity, would that be like moles ion?
Moles per liter.
But is
Moles
it
per liter.
Moles of what?
That's a good question. I would say moles of sodium sulfate per liter. And what this is for, what we're trying to handle is trying to handle that idea that if we add more salt, our solubility increases. Other things are off. And that's what it's after. It's not after, we're not talking about those big long expressions where we convert one amount to another amount. That isn't what this is. It's not a concentration in that aspect. It's an ionic strength. Maybe, yeah. Okay. Activity and activity coefficient, gamma. Okay, that's the little gamma. When is the concentration of a compound the same as its activity in a solution? Now this whole activity thing, if we used activities, everything's fine. Jose, everything's fine. If we add salt and talk about what's the solubility of this insoluble compound, and the solubility is supposed to increase, if we use activities, we'll predict the right answer. Okay? That's what activity is really driving at. But activity, and if you use concentrations, you get the wrong answer. So the question is, when does it not matter? When is the concentration of a compound the same as its activity in a solution? Gamma equals 1. Gamma equals 1 for, remember I said it didn't matter for what compound about 20 minutes ago. This compound, it didn't matter. It wasn't an ion. Sugar, right? It didn't matter. It's an ion. So there is no activity equals concentration. It's an ion. Gamma equals 1 for it because it's neutral. There's no ion there. So I would say for neutral compounds. There's no ions in it. That's the whole idea, the whole reason why there's an issue with it, why there's a problem. Ions interact in solution. You end up with these effective concentrations. They're not true. Okay, they're effective just to get the right answer. So is it better to use activities or concentrations in the real world? Well, obviously, activities, right? Okay. And here's how you get them. Here's the equation for it. Okay. The activity for some compound C is the concentration of this compound C times its activity coefficient gamma. Okay? What would the activity coefficient be if the solution were acting ideally? Oh, it's another way of rewording the whole neutral thing, right? Ideal solutions, there's no ions, there's no interaction. Okay, so that'd be 1 again. Just another way to reword it. Write the KSP expression for the below reaction with and without activities. Okay, so write the KSP without activities. We're not solving anything, we're just writing the expression. Then write it with activities. Right? Write it with activities, write it without activities. So Mariella, what did you write for without activities? The PB, yeah, but in the concentration of it, right? PB plus 2, but you need the concentration of it. Okay. Yeah. Squared. All over 1. Okay. Naya, what did you write for with activities? With activities. How would you write the KSP expression? Anybody help? Kevin, how would you write? Gamma, not gamma C, gamma P. Okay, I thought he was going to write this, right? But this way, what he's saying is even better, right? I thought he was just going to say the activity, right? A little PB plus 2 on that. But this is much more useful, the route he's going. So keep going, Kevin. Finish this. It's good. And it has to be squared all over 1. Okay. Did the KSP number change? No, that's the KSP. That's for that compound. It's in tables. That's not going to change on you. So hopefully what you're seeing out of this, what's coming up, nothing really changes. We just have to figure out how to put in these fudge factors. It's activity coefficients. And make sure you square it when you're supposed to square them. They're just going to be numbers. Yep.
Are gammas, is that like given?
Good question, Jamie. Here it goes. How are we going to get that gamma? Led into the next one. Okay, there's 2 ways to get it. Here's the first way. Log of that gamma, the activity coefficient we're after, is a negative 0.51 z squared, square root of mu, all over 1 plus alpha, square root of mu over 305. And you have these programmable calculators, it probably wouldn't be that bad. Except the problem is you have to look up. Now the z we already said is what?
C is the charge.
The charge. And let's say we're looking, we want to know the activity coefficient for the calcium or something. I don't know, whatever it is. So that's no big deal. But you have to look up alpha. Now the ionic strength, we already know how to calculate that, so we have that part. We have that equation for it. But this guy, you got to Google it. And good luck on that, because no one does it this way. It's the hydrated radius of the calcium ion. Now what the hell is that, right? But it has a plus 2 charge. So all the little, remember water's polar, the little partial negative is on the H or the O's on water. The little partial negative charge is on the O's, on the oxygen. So they're all going to be oriented around the calcium ion, and there's going to form this kind of little structure around there. How big is this bloody thing? What's the effective size of that calcium ion? It's not that calcium ion. Look how it's hydrated for, I don't know, molecules perspective for miles, right? But no, so we're not going to use that equation. You could, though. Okay? We're going to use tables. We're going to use tables to get our activity coefficients. Okay? And I scanned this is the one from your book, and it's not in there because I just did this, but you have it in your book. And notice how they grouped some ions, right? And they just grouped them because it's a lot, otherwise they'd just be repeating themselves. Because if two compounds have the same charge and really close to the same hydrated radius, they're going to have the same activity coefficient. So they kind of just try to make this table as small as they possibly could. And that's why they're kind of grouped that way. So you can see here, like here's all the charge, everything has plus or minus 1. Right? It doesn't, and then the ionic strength is over here. Okay, let's see if we can do a few of these. So again, what we're after are these guys, right? So we can solve X and ice. None of that changed. We're just introducing fudge factors. How do we get these activity coefficients? Determine the activity coefficient for each ion and ionic strength. Okay, so somehow earlier already, they already calculated the ionic strength for you. They used that equation to get the ionic strength. They want to know if the ionic strength is 0.05, what is the activity coefficient for magnesium? Okay, so you go up to the chart. Let's see whose eyes are good. Eric's nice and close. Okay, the ionic strength is 0.05, right? Okay, so you're this column. And we're after magnesium plus 2. So we should be in this area.
0.52.
He says 0.52. Oh, yeah, right there. Right? So that's it. Okay. But you know, what are the odds of your homework giving you stuff that's going to fit nice on this table? You know it's not going to happen. It might, but I don't think it's going to happen very often. You have to use the I word. What's that again? Interpolate. Interpolate. Okay, here's a good one. Hydrogen ion with ionic strength 0.003. Why is this important? Heck, this could be a pH measurement, right? Because pH is a negative log of the activity of the hydrogen ion if you really want the right answer. So you plug in its concentration times the activity coefficient of hydrogen ion. So, and pH is extremely important. So this is a good example. Hydrogen ion with ionic strength 0.003. 0.003 must not be in that table. Yeah, see, it's not. Okay? So we interpolate. So how I like to do it is, okay, let's see. I got to get into my little mode here. Okay, I make a little table. And it's a lot easier for me not to make a mistake if I make my little table. So the ionic strength is 0.003. So I'm going to put that in the 0.003 row. Okay? This is the one I'm after. So what I'm going to do is I'm going to find the 2 points that are closest to it, that are bordering it. In other words, let's find hydrogen ion up here. Here it is. And 0.003 is right in the middle, right? 0.003 is right in here. So my 2 points are pretty much going to be this ionic strength 0.001 with 0.967. That's going to be right below it. The one above it would be what, Christine? Would be what? Would be the points right above it. 0.005 and 0.933. All right? So that's what I'm going to do. Remember those numbers. Some of them are 0.001, 0.967. 0.001, 0.967. 0.001, 0.967. Okay. What were the other two? 0.005? Oh, wow. All right. So now we just pretty much, the unknown activity coefficient interval over its known interval has to equal the unknown ionic strength interval over the known ionic strength interval. So just plug them in. Unknown gamma interval. And this is where the table helps me. Because if I just like to start on one side, right? The unknown activity coefficient interval, 0.967 minus the question mark. That way I can be consistent when I do the unknown ionic strength interval. I'll take this one minus that one. Okay, that way I don't screw up. Because otherwise you're going to screw up. You do one minus one side and then the other side. Okay. So the unknown activity coefficient, 0.967 minus question mark. The known activity coefficient interval, there it is, 0.967 and 0.933. The unknown ionic strength interval, so again, I'll just go from left to right, 0.001 minus 0.003. And the known ionic strength interval, 0.001 minus 0.005. And another advantage is I've done this before, and plus there isn't an ionic, well, I guess this is the advantage. There's no negative activity coefficients. So you don't have to worry about taking the higher minus the lower. It's going to work out. Right? There's no negative activity coefficients. We have one equation with one unknown. Let's see what it is. Okay. If you're good with parentheses, you can do all this in one step. Did you get an answer? Whatever you get, go back up into the table and make sure it makes sense. Whatever you get, go back up into the table and make sure it actually fits. Right? And well, you don't really have to go back to the table, I guess. You can just look right here. Does it fit? It needs to fit. That's what I got. I got 0.952. Good. Did you get 0.95? Okay. You should be getting 0.95. And it fits. Right? 0.95 fits. Okay. I got a positive number. Now you messed up somewhere. Right? What I did is, I guess I've gotten good at this because I've done it so often. I see an equation, I see where to start. The first thing I'm going to do is I'm going to do this part first because I don't even need parentheses. I'll take 0.001 minus 0.003. Hit equals. Divide by, now I'll use parentheses, divide by this. Hit equals. Multiply by this one. Right? Because he has to go up on top. Multiply by that one in parentheses. Hit equals. Last step, subtract 0.967. And I will get a negative answer, but have a negative question mark. Okay. So if you're going to do it all in one single step like that, your life is, if you can practice it, your life is going to be much less frustrating, and you'll get the right answer more often.
The answer should be negative, but because it's minus,
You're going to end up making it positive. So the answer shouldn't be negative. The answer is going to be positive.
And the calculator comes out negative.
Yeah.
Still, I did it all in one step.
Okay. Oh, you did? Okay, you got 0.95.
Negative 0.95.
All right. Excellent. Okay. Non-ionic compounds in water. For non-ionic compounds in water, for non-ionic compounds in solution, the activity coefficient, gamma, always equals
1, 2.
confidence. It's what? It's 1. There's no activity problem anymore. It's not an ion. All right? Everything we've been doing before works great. We don't have to worry about these fudge factors. Okay. Calculate the ionic strength. So they want the ionic strength of 0.0002 molar lanthanum 3 iodate. Assuming complete dissociation at this concentration, no hydrolysis to make, so there's no complex ions. You really don't even need to worry about this. right? But just kind of disregard it. But it's there because it technically needs to be there. Okay? Calculate the ionic strength of that compound. So remember what the equation was for ionic strength. Figure out what the concentrations are of all the ions, their respective charge. To do this question, that's a good point. Here, someone was mumbling about it. You have to assume that it dissolves 100%. You have to assume that, right? So if you do that, what's the concentration of the lanthanum 3? 0.002. Oh, sorry, 222. And the concentration of the iodate? 3 times it. Good. I think that's really the only trick there is, right? And recognizing what the charges are. Okay. And I guess another strong hint is just by looking at this. You have 3 iodates for every 1 lanthanum. So you need to multiply. You have 3 times the number of iodates as you do lanthanum, right? Just by going by the chemical formula. So you have to. This has to be 3 times as concentrated. Okay. So 1/2 the charge. Lanthanum is +3, or sorry, the concentration, 0.0002. Charge squared, and the iodate okay, and then you get your answer. .0012? 0.0012? Okay. Sound good? All right. See if you can knock these out and we call it a day. Find the activity coefficient of each ion at the indicated ionic strength. Sulfate 0.01 molar and hydrogen ion. Yep. Several folks got 0.001 too. Did you get that, Andrew?
Yeah.
Okay. Find the activity coefficient of each ion at the indicated ionic strength. Man, you guys don't have a table either, do you? Right? Okay, so memorize this. Ionic strength and the ion. Everyone got it pictured in their head? All right. Here's your table. Can you even see it? Where's sulfate's at the bottom, I hear. Should be ±2. Oh, yeah. I hear 0.66. Oh, it's even on the table. Isn't that nice? 0.660. Easy one. 0.660. All right. Try this one then. Okay, you got it? It's hydrogen ion, and it's 0.03. Hydrogen ion and 0.03. Now you need the table. Hydrogen ion and 0.03.
Can we get this interpolate?
And interpolate.
Can we get that equation on our sheets?
No, you're not going to get the interpolate equation. Because all it is just one thing over the other. And you had to do it once already in a previous test.
But we did it a different way that time.
Did we?
We did it with like subtraction. Like.
I don't remember. We're doing subtraction.
Maybe I'm just not seeing it.
All right, so try to get it. Oh, we're about out of time. But you can set it up so then when you do go home to do your homework, you can see what to do. Right? I would make that little table. That's how I do it. You don't have to, but I suggest it.
We do have the handy dandy table on the next page.
Oh, it is?
Nice.
Oh, I didn't even know that. Zach, speak up, man. Have a good day.
What's the definition of activity?
I would call it the effective concentration. I think that's how I would define it. Because when we think of concentration, we think of, oh, that's the number that we use to plug into pH and all these expressions to get the right answers. Concentration isn't good enough. You have to plug in the effective concentration. What's the concentration that's really active? So it's your concentration, but you have to multiply a little fudge factor by it.
So is that how much will like react or dissociate?
Well, it's kind of like if you have 0.2 molar as the concentration. Well, to get the right answers, you really need to plug in 0.23 molar. So you need to multiply your concentration times the fudge factor to get the right answer. And that fudge factor is the activity coefficient. That's how I look at it.
Like that, like those uncertainties and stuff like that.
Well, not really. Not really.
In terms of like concentration.
It's not really an uncertainty. It's a number that you put in to your expression so that you get the right answer in real life. So
We'll have to get an early start and get ready for the next one.